Hello viewers, today's video will be a little bit different. Since I do a lot of ARM Cortex M development, I was thinking that I would share some features from this processor with you, and today I will be explaining what bitbending is and why you should use it in your projects. So please let me know down below in the comments if you like this ARM explanation series, so I will try to make next part. So what is bitbending? It's a way to quickly and safely change only one bit in your variable or in peripheral, which means you can change a single bit in your RAM, in your static RAM memory, which is variable, or you can change a single bit in some peripheral register. Usually if you have some flag and you have bits with different meanings on different positions, you use this OR symbols or AND, or someone can use XOR, and you write a bit to your variable, so you will know, for example, that in your embedded systems the door is open, the light is on. So you usually do it this way, where you are ORing your variable with a bit which you would like to set, or you can alternatively write it like that way. And this is a typical read, modify, write approach, because when you compile this code, the compiler does this. It loads from R7 address the value to register R3, then it will make OR arithmetics on your register R3, right now with number 2, which is this number, and then it writes the R3 register back to the memory to this position. What's wrong with this approach? The first thing is then you use 3 instructions to set just one bit. You will see later that it's possible with just one instruction. And then if you have some interrupts, there are possible race condition which can occur if interrupts is firing here or here, because the interrupt cannot interrupt atomic instruction. The instruction is this one or this one or this one, and the only way your program can go wrong is when, for example, here is triggered the interrupt and your flag variable is read or changed, then things can go wrong. So if you can do this operation with just one instruction, you are safe. Usually if you do this readmodifywrite, you somehow, for example in Atmels, you disable interrupts before the change and you enable interrupts after your change. So bitbending in ARM processors will work like that. You can then use your variable just to set a single bit. I named this variable that this means bitband. This is name of the variable flag, and _1 means that it's the first bit, because indexing starts from 0. And the advantage of bitbending is also you can use it in your if statements. So instead of ending the variable and the value, you can just point the if statement to the address. So this was a simple explanation. I hope you're still here. Later I will move to practical compilation and disassembly examples of the code. So I will show you how the code is improved with bitbending. So the bitbending is not available in all ARM Cortex processors, ARM M, because ARM Cortex M0 Plus is option. The bitbending is optional. And now I think we can move to a little bit coding and assembler listings. But first I would like to show you which architectures has this capability before ARM, because when I was writing code for x51 processor, then this processor is actually able to manipulate individual bits. So you could use set bit or clear bit instructions, and this will take also 1 clock cycles. So you can change, this is a very good example, you can change individual bits in this area of your RAM on the chip. Also you can change some bits in registers, and also you can change bit in port registers, so you could blink an LED with a single instruction. If we take a look on AVR instructions, you can also use bit set and bit clear instruction, set bit and clear bit, but these instructions are only working on registers, so you can enable or disable timer. Actually you can, I think, change the output pin only 1 bit, so it's possible to blink an LED with these instructions. And when we move to the ARM, then you can see that you can also manipulate individual bits in your SRAM and individual bits in peripheral memory. Of course, there are some restrictions, like only 1 megabit, the lower part of your RAM. So only 1 megabit can be bit bendable, and only lower 1 megabit of your peripheral address space is bit bendable. And it works like this. I found this nice picture. Then if you take a look, then the static memory starts at this address, 2 and a lot of zeros, and this is a pretty picture which explains that if you would like, for example, change this 1 bit on this address, the first bit, you can write number 1 to this address, 28 something 1. And you see this mapping, and with this mapping you can change any bit at this address and the subsequent addresses. So this part of memory is some kind of virtual memory, and if you write a word which is a 32-bit number to this address, this bit will be 1. And it works the opposite way too. If you write a decimal number 4 to this address, that means that the bit on the position 2 will be set. Then if you read a value on this memory space, you will read 1. So let's move to the practical examples. I would start with readmodifywrite example in AVR architecture in Arduino development environment. The first thing is that I would need assembler listings of this compiled code. So I would need to see what was compiled. I can do this. I cannot do it directly in Arduino, but I can find where the binary is compiled by ticking this checkbox. So this is something like show more information during compilation. And what the program basically does is then I have some variable, and I would like to send the first bit in this variable, and then I would like to clear that bit in this variable. So I will compile this example. And here you can see where the ELF file is located. And if I use object_dump command, I can create listings. So this command was compiled in this 3 instruction. So the first thing is that it loads a variable from memory 100 hex into register R24, then ending this register, and it's writing it back. Now there is a return, and this goes again. Now we maybe ask why there is only one readmodifywrite when I have here two commands, set and clear. And that's also because of some optimizations. So because there is end command, and I see here the fd value, I immediately know that this is the command which is compiled and this one was ignored. And the compiler is trying to be a little bit clever, and it sees that this was the last command to set the variable flag, so it will ignore this first one. One way to force the compiler to not ignore this command is to write a volatile in front of this variable, which means for compiler that it doesn't try to optimize any instructions, any commands to this variable. So I will recompile this once again, then generate new listings and take a look at output. And now you see that I have both instructions. So this ORing instruction is here. Yeah, you can pretty clearly see that there's OR with the number 2, which is this value, and it's written back to the memory, and then the second command is again loaded to the register. It's masked and written back to the memory, and it's going over and over again. So unfortunately on AVR you are not able to change the bit in your memory with the one instruction. And as I said before, this can be dangerous because if you have some interrupts which also works read or writes with this variable, and this interrupt will trigger when your processor is here, or here, then a race condition can occur. So usually you do what I have already written. You disable interrupt and then you enable interrupts again, which can work, but it's not optimal all the time. Okay, so now I've started Atomic True Studio for ARM. This is IDE based on Eclipse. It's quite good. It's free without any code size restrictions. So I have the same example like I had in Arduino IDE on AVR processors. This will be compiled for ARM Cortex M4. This is the board I'm using. So it's a Nucleo board. It doesn't matter which board I use. You wouldn't see any blinking lights. We will just focus on disassembly of this code and on single stepping of the commands. So first, I have also defined my flag. This time is 32-bit value because it's a 32-bit processor instead of AVR. So let's start this example right now. And here you can see on the right that it's pretty much the same like with Arduino. So this is read, this is modification of the value, and this is writing back. So as I've said, there are two bitband regions. So one is for peripherals, one is for static RAM. And so I have to use two defines, one for peripherals, one for RAM. We will use just the RAM1. This is the expression you have to use to map your variable and bit to the bitband address. There's a lot of information in datasheets and different websites how to compute this. And I will create a variable which is pointing to the bitband region of this variable on this bit. So this should work. Okay, if I take a look at this BB flag, or what's the address, you can see that I'm not sure if it's possible to look at bitbending in your development environment, because this bitbending is in the core of the processor. Another thing is that if you use DMA, you also cannot use bitbending, because it's really the bitbending computation is really only in the ARM core, not in DMA peripherals. So I single step this, and you can see I changed the value, and now it should go back to 0. Maybe I can display hexadecimal it. K2 and back to 0. So this is the old one, setting that bit and clearing the bit, and this is the new one with bit bending. So now let's take a look closer on the assembly output, which is here. So if you take a look, as I said, there's read modify write approach. I can enable instruction stepping mode, so I will single step by an instruction, not by a C command. Okay, the setting, this is clearing, and here you see again the setting and clearing with a bitbend. Now maybe you are asking why there are also 3 instructions, because the old approach has 3 instructions, and the new approach, which I'm saying is better and faster, has also 3 instructions. So what's the difference? What's the improvement? Here is still possible to have race condition if your interrupt fires here on here, and in this bitbending command it's actually safe, because here we are reading the address, the virtual address, this virtual address. Here you are setting 1 to your register, and this is the atomic instruction which writes your number 1 to the virtual address, not to the physical. And so this is actually interrupt safe approach to set a bit in your flag. But as you can see, it takes 3 instructions, the same number of instructions like the old approach. So why I was saying that it's quicker. Actually, I have to help to the compiler a little bit, so the compiler will know that this address, which is loading every time, is constant and it's not changing at any time in the code. So that way it will compile to only 1 instructions, which is the last one, store. So let's do that. So the first thing I would need to do is enable some compiler optimization. Usually I will set optimization for whole project, but to make the things quick, I set the optimization just for the file which I'm changing right now. I choose the smallest optimization and the optimization which is best for debugging. So during the single stepping, the code will move forward and not skipping back to different places. Okay, now let's try if it already creates 1 instruction per 1 line. And you immediately see that something is wrong because it's not stopping on instructions. And that's understandable because the optimization is working that the optimizer looks at this loop and sees that I'm writing to this variable, but I'm actually not reading this variable anywhere in the code. So optimizations are trying to be clever, and it completely throws away these commands. If I can stop this loop, then I can take a look. It's jumping on 39E, which is this. So it's doing practically nothing. So again, to tell the optimizer to not optimize these values, I have to write volatile in front of my definition, and also volatile at my definition of bitbang flag. So let's try again. Okay, now it stopped. But now with the bitbending, I have only one store instruction, which is perfect. So now watch this flag and it will change with just only one instruction. So step, it's set to number 2, and now will be cleared, step, and it's cleared. So you can see it's now 3 times shorter and also faster, and it's done only with one instruction. I wanted to show you also blinking LED with these commands, but unfortunately it's not possible because when you take a look at this memory mapping, the GPIO peripherals are actually above this 1 megabyte region, so it's not possible to change output pin with bitbending. I'm not saying that it's not possible because STM32 can change 1 bit on your GPIO, but not with bitbend, but with a bit set register and bit set reset register. These two. So thanks for watching. I hope you're still there, and if you have any questions you can write them down below in the comments sections, and subscribing always helps and will motivate me to create another tutorials like that. So see you next time.